We've already seen a couple of times now that the function f of x equals x squared is not invertible. What I want to do is explore that a little bit and see if we can come up with a criterion for when a function is and when a function is not invertible. The problem, of course, here is that illustrated by these 2 points here. 2 and negative 2 square to give me the same thing. So if you tell me, hey, I did something and I got 4, and what I did was square things, what did I start with? I don't know. I don't know whether you started with 2 or with negative 2. And of course we saw if we switched the role of x and y and tried to solve uniquely for y, we weren't able to do that. Okay? So what's going on here is that there's a little bit of a double standard in our definition of a function. In order to be a function, each input has a unique output associated with it. And graphically, that's reflected in the vertical line test, that no matter where I put a vertical line, it's going to intersect, here's my vertical line, it's going to intersect the graph at most once. But it's okay if we have a function if there's a repeated y value. So that y value of 4 has 2 different x values associated with it. And when we first talked about functions, we talked about them as almost being like vending machines, where if you know what the input is, you know what button you pushed, you know what you're supposed to get out. I pushed the Coke button, I want a Coke. Okay? But it's totally fine for there to be more than one Coke button. There very often is, so that's 2 different buttons that should give you the same result. Well, functions work the same way. Okay. But if I have something like that, if I take advantage of that double standard so that there's a y value with more than one x associated with it, it's not going to be invertible. Because now, if I were to switch the roles of x and y, the point 4, 2 would be on the graph of the inverse relation. The point 4, negative 2 would be on the graph of the inverse relation. But then that's not going to be a function, because that would be 2 points whose x value was now 4, whose y value was not. So we say that a function is 1 to 1. We read that as 1, 2, 1. We write it as 1 dash 1. 1 to 1 means that each output, or each y value, has a unique x value associated with it. Okay, we only talk about things being 1 to 1 if they're already functions. Okay, so we talk about 1 to 1 functions. We don't talk about 1 to 1 graphs unless it's already the graph of a function. So it has to be a function, and then we say it's 1 to 1 if in addition to each input having a unique output, there's no double standard. Each output also gets a unique input. Okay, and we can test that graphically with the horizontal line test. Just like a vertical line picks out every point with a certain x value, a horizontal line picks out every point with a fixed y value. So here, this horizontal line at height 4 is intersecting the graph more than once. Okay. So the horizontal line test says that a function is 1 to 1 and thus invertible if no horizontal line intersects the graph more than once. Okay. So if we're given a graph, we can tell just by looking at the graph whether that function is going to be invertible or not. That function is not invertible because I can put a horizontal line at any of these heights. In fact, I can see the x-axis is a horizontal line, and that intersects the graph 3 times. Okay. So this is not 1 to 1, and therefore it's not going to be invertible. Okay. Notice that with inverse functions, we're switching the roles of x and y. When we do that, a horizontal line is everything with a fixed y value. If we switch the roles of x and y, that becomes everything with a fixed x value. That becomes a vertical line. So if you fail the horizontal line test, what that's saying is when we switch the roles of x and y, now you're going to fail the vertical line test and you're not going to be a function. So that's our test for whether something is invertible or not. One thing that's kind of interesting is if my function is defined on an interval, if there aren't any gaps in the domain, then you'll notice this fails the horizontal line test because it changes direction. We were increasing, then we were decreasing, and when we switch to decreasing, now we're retracing and hitting those same y values all over again. So it will also be the case that if f is increasing on an interval, it is 1 to 1 on that interval. And the same would be true if I replaced the word increasing with decreasing. Okay. Can't do both, but if it's just increasing or just decreasing, on an interval, it'll be 1 to 1. Now, it is important that I specified on an interval there, because here, there's a function that's increasing, and now it's increasing again, but it's not 1 to 1 because it jumped down to repeat those y values. Okay. So actually, let's put an open circle there. So this function would always be increasing on its domain, but it's not 1 to 1 because this domain wasn't an interval. It jumped so that we were able to repeat some y values. Okay. But if you're working on an interval and you're just always going up, you're going to hit some y values, you're going to go up, so then you're higher than them, you're not going to repeat those y values. The only way, if you've got a continuous graph that doesn't have any gaps in the domain, so no opportunities for it to jump back down, the only way for you to go down to repeat a y value would be to change direction and start decreasing. Okay. So that's our criterion for a function to be invertible, that it has to be 1 to 1. And you can see that graphically by looking at the graph of something. And if you've got a formula, you can sometimes see if you've got x squareds in your formula, it's not going to be invertible. Basically, any even powers are not going to be things that you can undo. And if you've got just a set of ordered pairs, you just have to check. So let's try one example like that. Let's say I've got the function 1, 5, 2, negative 3, 4, 5. Now, that's a function because each input, my inputs are 1, 2, and 4, each of those inputs has a unique output associated with it because the inputs are not repeated. But it's not going to be 1 to 1 because that y value of 5 has 2 different x values associated with it. So we would say this is not 1 to 1, so it's not invertible. Now I can, again, form the inverse relation, but I cannot form the inverse function because when I switch the roles of x and y, I get something that is not a function.